Hi, everybody. Welcome. Good morning. My name is Luis Betancourt. I'm the director of the Mansueto Institute. I think I know most of you, but I'm not sure who's there necessarily. So welcome to our sort of brunch version of our lunch colloquium. And today, I'm pleased to introduce the presenter, Fengli Xu. He's one of our sort of relatively new fellows. He's coming from Tsinghua University in China, and because of the pandemic, he's delayed his arrival here in Chicago, and so this is also why our talk is a little bit earlier today. But next time you hear him speak, he'll probably be in Chicago, and we'll do it at lunchtime. So Fengli comes from a background in engineering, but really in data sciences. So he's kind of an example of sort of a new generation of researchers that work a lot at the interface of engineering, data sciences, and social phenomena in cities. And he's done really interesting work with mobility, machine learning, and today he'll be telling us also about some of the implications of these very detailed high-frequency data about human behavior as they relate to issues of transmission of diseases, and particularly COVID. So this is a little bit his introduction to our community, and I want to also take the opportunity to welcome him in that quality to all of us. So I hope you get to meet him a little bit through the talk, and he is very welcome also to be in touch with you via email and start discussing any issues of common interest. So Fengli, without the last thing I want to say is that he's also associated with the Knowledge Lab and James Evans in sociology, his co-advisor. So Fengli, the floor is yours. Thank you for being here, and we look forward to your talk and to having you in our community.
Okay, thanks for the introduction. Yes, sorry to change your lunch talk to the brunch talk, but I should have been to the US sooner, but it was delayed by the pandemic. Yeah, but I got all of the things sorted out. So hopefully I will reach Chicago by the end of this week. Yeah, and maybe we will have a more interaction after that. So if you notice, I have changed the title a little bit, so that I want to also include some of our previous and ongoing work in the end of this talk, so that maybe we can try to do some discussion and inspire some collaboration, perhaps. I hope this is not a false advertisement. Okay, so my topic is human mobility in urban space, and we have focus on the COVID-19 risk and the city structure. So, okay. First, let me give a quick introduction to the background. So since the beginning of 2020, so the COVID-19 pandemic has rapidly swept over the globe. I think I don't need to remind you how serious is this pandemic. And one recent paper, actually that's one of this Lewis paper, showed COVID-19 attack rate increases with city size, that's the population. So therefore, it is particularly important to understand how the disease transmits in the urban space. And however, the growth curve of COVID-19 confirmed cases in different cities are very complicated and significantly different. For example, here we randomly selected several counties in the United States, and these are the growing curve of the COVID-19 confirmed cases in the initial days of these 4 counties. We can see that there are very different growing curve. One of them is like the S shape here, and we also have some exponential shape here, and also some more like a linear curve here. So, however, the classic epidemiological model, so for example, like this SEIR model, so the S means the susceptible, and the E means exposed, and the I means the infected individuals, and the R means the recover or remove individuals. So this classic epidemiological model, SEIR, it cannot characterize this complicated growing curve. So it basically only have 2 scenarios. So if the R, meaning the reproductive number, is larger than 1, then it will the infected persons, the green curve here will actually grow like an exponential in the beginning, and then will like become a S curve because all of the population are infected. Okay, so but if the R is equal to 1 or less than 1, then the pandemic will not spread. It will be like a flat curve because it will just move through the population. It will not generate more cases by days. So the existing models cannot predict, can only predict this exponential growth or no growth, but it cannot adequately explain the complicated real-world curves. And one of the recent work in last year tried to explain the sub-exponential growth of the COVID-19 cases with a new model called the SIRX. So they proposed this self-containment mechanisms in the models. Basically, this model will remove the susceptible population with this parameter kappa zero. So they find that the sub-exponential growth of the confirmed cases can be reproduced with the exponentially fast depletion of the susceptible population. Okay, so this is the curves they reproduce. So the pink line here is exponential growth of the cases, and their model can reproduce a sub-exponential growth, so more like a linear or the scaling or the power law, right? So, however, this model provides a mechanism at the macro level, like how to control the susceptible population, but it cannot explain the micro foundation like from the human behavior perspective. So here we derive our first research question we want to answer, that is how to rationalize the distinctive growth curves in different cities. Okay, and beside of the growing curve, we also noticed a prominent superspreading phenomenon in urban space. So this figure is from a fine-grained contact tracing study in Hong Kong that they find a prominent superspreading phenomenon where a large percentage of the secondary cases are traced back to disproportionately small percentage of locations and patients. So we can see in this probability, this distribution figures here, we can see that most of the confirmed cases, they generate 0 secondary cases, like more than 60% of confirmed cases, they generated zero secondary cases. And many of them are only 1 secondary cases or 2 secondary cases. But there are a few patients, they will generate a large number of secondary cases, like the big cluster here. Here is a bar, and here's a temple, and here's a white. So there is a very prominent superspreading phenomenon in the COVID-19 pandemic. So previous research tried to use this individual variation to explain the superspreading. Specifically, they use this individual reproductive number. That is the number of secondary cases generated by each individual. Okay, so they use this individual reproductive number to predict. Okay, they predict it to follow a negative binomial distribution with the mean value of R0. That is the mean reproductive number, and a dispersion parameter K. So the prominent superspreading effect will be reproduced when the K is close to 0. So here is the distribution of the individual reproductive number given different K. So we can see that when the K is close to 0, then the distribution is very uneven. There are a small portion of the individual will have a very large number of the reproductive number, but if it is a large, like 4 or 1, it will be like more flattened. Okay, so this is Okay. This is the measurement of some previous the right figure. So the right figure is the measurement of some previous pandemic, but this paper is published in 2005, so there's no COVID here. So we can see that the SARS have a very small dispersion parameter, so that like more than 80% of the cases are generated by the top 20% of the cases here. So it is a very prominent super spreading. We have a similar scenario in our COVID-19 here. Okay. However, the recent study showed that the super spreading events are actually fatality. So if we go back to the previous slide, so the super spreading will only be will only occur if the k is less than 1. But if the k is less than 1, we will have an exponentially decaying tails here. Okay, this we have an exponentially decaying tails here. However, the recent study this year find that in this paper find that the super spreading events are actually fatality. It means they are extremal yet probable. Okay, this is the distribution they find. So the yellow dots here are the prediction of the negative binomial distribution. That is the prediction of the previous paper. Okay, the blue dots here are the empirical data. Okay, they find that it can be better fitted with a scaling distribution, like there are more fatality. It means the extreme case, the super spreading case here are more probable than they think. And a case study in Singapore linked the super spreading events to the dormitories of migrant workers. So I think this real findings indicates that we can only consider the super spreading as a probability, but it should be considered based on, we should try to develop a more principal mechanism to explain, to systematically explain the super spreading events in urban space. It is not like only the super, it's not only probability, like the individual variance, variety, but it will be also, it will be more, you also related with the city structure and yeah, this kind of stuff. And various of non-pharmaceutical intervention policy have been implemented by local health authorities to combat the coronavirus. I think we all know, like the compulsory mask wearing, mass COVID-19 testing, and mobility reduction policy, different kind of non-pharmaceutical intervention. So the third question is how to consider the adoption of NPIs in epidemiological models. So here is the three research problem we want to address in this research. So the one is how to rationalize the distinctive growth curve in different cities, and the second is how to develop a mechanism to explain the super spreading events, other than only based on the probability distribution, right? And the third is how to consider the adoption of NPIs in these epidemiological models. So this leads us to our key idea of this research. That's the classic epidemic model. There's one key underlying assumption. That is the homogeneous population mixing. So for example, take Chicago, for example. If we consider the population is homogeneously mixing, then everybody have like an equal probability to establish a link or transmit the virus to the others. So it's like a fully connected network. However, in this real world scenario, this is the more likely the mobility of each individual, right? Some of them, different people are active in different parts of the cities, so that some of them are more likely to transmit the virus between them, and some other individuals are less likely. So this motivates us. Maybe we should increase the expressiveness of the epidemiological model by considering the intra-city mobility behavior, the fine-grained intra-city mobility behavior. As a result, we try to propose a mobility-driven meta-population model here. So in this model, instead of considering the whole city as a whole, as a pole, we segment the urban population into a group of spatially separated subpopulations. We call it like a neighborhood. So these neighborhoods, they interact with each other based on a mobility behavior. And in each subpopulation, we maintain a standard SER model. So look like this. So so the susceptible population of each neighborhood, we have a probability to become exposed or infected population, and it will also have this input means the exchange with other neighborhoods. Okay, and so in all of these categories, they have this exchange with the other neighborhoods. Okay, the SEIR states interaction are due to the mobility behavior predicted by our model. And we also use a learnable infection rate here to consider some intervention policy that might they might impact on the infection rate, like a social distancing or something like that. And then we also put a learnable remove rate gamma here, so to consider the to model the policy like mass testing or quarantine, or something like that. So in terms of the intra-city mobility model, some of the previous research use the empirical mobility data in their paper. So, but these fine-grained mobility data are actually very difficult to obtain, and they often have very serious privacy implications. So here we want to use a mobility model instead, trying to approximate the mobility behavior in urban space with a model. And here we use the gravity model that was inspired by this Starvis laws that state the number of persons going to a given location is proportional to the number of the opportunities at that location, and inversely proportional to the number of intervening opportunities. So based on these inspirations, we predict the number of mobility, we predict the mobility flow between two neighborhoods as proportional to the population size of those two neighborhoods, and inversely proportional to the distance between them. So that's like a gravity model, like the Newton's gravity model. And we also have one learnable parameter here, m. It can help us to control the mobility level of the whole city. Okay, so to summarize, our model have several parameters, but the other parameters the other epidemiological parameters are set according to recent medical research. And we only have three learnable parameters here. One is the infection rate that try to consider different implementation of the social distancing policy. And one is the quarantine rate that try to consider the different capacity of testing and quarantine. And the third one is the mobility level. They try to control the intra-city mobility behavior. Okay, so here is how we optimize our model. So the initial population distribution is derived from the open source WordPop project. So this project provides fine-grained population distribution around the globe for most of the major cities. Okay, And we used the daily confirmed cases released by Johns Hopkins University from March 8th to April 30th in 20 US counties as our ground truth. And we optimized our model. That is, we optimized the 3 learnable parameters with a Bayesian optimizer. Okay, with the objective that to minimize the INSE with ground truth. And then we also set a policy change point. So because the most of the intervention policy and the national emergency are put forward, I believe, in the late March in US. So we set the April 1st as the policy change point. So to learn 2 sets of parameters before and after the change point, so that it can reflect the behavior change before and after the intervention policy. Okay, so here are some is the experiment result of our models. So the red dots here, the red dots in each subfigure denotes the ground truth of confirmed COVID-19 cases in these 20 US counties. Okay, and the blue curve here is the prediction of our model, and the shaded area here is the 95% confidence in interval, and the green curve here is the baseline of the standard SER model. So we can see that our model, the blue line can fit the red dots pretty well in all of the counties. And despite that, the county has very different curves. Like in the first class, they are more like a convex curve, a convex curve here, and the exponential curve in the second classes and second categories, and maybe a more like a S-shaped curve in the third categories, and more like a linear curve in the fourth categories. Okay. And it significantly outperformed the baseline of standard SER model. So with the R2, the R square of the fitting is reached up to 0.99. So we also performed some theoretical analysis on our model. So we can consider 2 extreme cases. So we can consider one extreme case that the mobility is very intense, so it's completely free. Then we let the M, the parameter that control mobility level, to be infinite, to be very large. Then our model will be equivalent to the infection of our model. The infection predicted by our model will be equivalent to the linear sum of a set of homogeneous SER models in each neighborhood. So we can theoretically prove that. So in this case, therefore, it is equivalent to a standard SER model. So as we know before, the standard SER model can predict the exponential curve, right? In the exponential curve of the epidemic growth, or S-shaped curve, if it is yeah. And if the mobility is completely banned, if we set the M to 0, then the infection will be limited to the initially infected neighborhood. So as a result, the effective population, it means the population the virus can reach is significantly smaller than the whole population. We have this NEFF significantly smaller than N. Then we can prove that it is a equivalent scenario to this SEIRX model previously proposed. So in this case, we can also reproduce the sub-exponential growth of the COVID-19 cases. So in this theoretical analysis, we can show that the standard SER model and the SIRX model are actually 2 special cases of our model, and therefore by controlling the mobility parameter M, we can reproduce the growth curve ranging from exponential to a sub-exponential, maybe like a convex curve or a linear growth curve. Okay, so here is some experiments to confirm our theoretical analysis. So we can see that in different transmission scenarios, so that's the so we can consider 3 different transmission scenarios. That's the remove rate divided by the infection rate. So this number, the smaller this number is, it means the transmission is more severe, because the remove or hospitalized is outpaced by the infection. Okay, so we can see that in different scenarios, we control the mobility level with like 10% or 80% of the real world mobility level. So we can see that in different scenarios, the shape of the growth curve can be significantly different when we use a different mobility level, when we can consider different level of mobility reduction. But there, where the low mobility level obviously leads to a linear curve, and the high mobility level leads to like more exponential and the S-shaped curve that's consistent with our previous theoretical analysis. And we also analyze, show the predictive power of our model here. So here we let our model to predict the confirmed case after 14 days of the model fitting. The confirmed case after 14 days. Okay, we can see that okay, the acceleration here is number of reported case, the ground truth, and the white legend here is the number of predicted cases by our models. So we can see that the normalized root mean square error is reduced to 0.29 compared to 7 of the standard SER model. So the prediction is pretty accurate. Yeah, in different cities. And we also show how our model can reflect the real world behavior change. So in this figure, the X dimension shows the mobility reduction we estimate in real world data. That is calculated based on the Apple mobility report. So so the 0.1 means there's a 10% mobility drop before and after the policy change date. Some of the countries even have a positive mobility change because they have their mobility reduction begins more earlier than the policy change date we choose. Okay, and the white label here shows the estimated mobility reduction based on our model. So that is calculated based on the n parameter in our model. So we can show that there is a very strong correlation between the estimated mobility reduction and the actual mobility reduction. It means our model really capture the behavior change, or should we say the policy adoption in different cities. And okay, in the second part of the experiment, we try to investigate the super spreading phenomenon in urban space. So in this figure, we show the distributions of infected population and the secondary infections in different neighborhoods. Okay, so the neighborhood is ranked based on the infectee and the infector ratio, and the y-axis here is the cumulative distribution function of the infected population and the secondary infection. Okay, so here we have 2 points, the 0.8 and the 0.422 point here indicates the bottom 80% of neighborhoods. The bottom 80% of neighborhoods only have 42% of the overall infected population. Only have the 42% of the overall. So in the other words, so our model can successfully reproduce the super spreading phenomenon, where the top 20% regions concentrate 85% of 58% infected individuals. The orange line here, with a Gini index of 0.55 and 69% of secondary infections, the blue line here. So we use the Gini index to measure the unevenness of the distribution of the infected and the secondary infections in on different neighborhoods. So the larger the Gini index is, means the more uneven the infection is distributed. It means a more severe, a more prominent super spreading phenomenon, perhaps. Okay, here we try to analyze we try to investigate the origin of this super spreading phenomenon. We try to put forward a hypothesis. We can consider several counterfactual scenarios. Several counterfactual scenarios. So in this scenario, we change the epidemiological model to an even population distribution, even urban population distribution. It means the city population are distributed evenly on each neighborhood, and we use a random movement among the neighborhoods. So in this counterfactual scenario, we can see that the super spreading phenomena are completely gone. So they distributed evenly on because they're close to this y equal to x function. So that they distributed evenly on each neighborhood. So the super spreading phenomena are completely gone. However, if we consider the scenario that there is an uneven urban population distribution, but if we change the mobility model to random movement, so that's the subfigure A here, then we can only explain a small portion of the super spreading phenomenon. So the curve is more close to the y equal to x here, and the Gini index is much smaller. It's only 0.198. And if we consider the scenario that we have an uneven urban population distribution, and we only keep the distance factor in our mobility model, remember that our mobility model have two factors. One is the distance factor. So the traveling probability will inversely proportional to the distance between two neighborhoods. And the other factor is the population. So the traveling probability will positively correlated with the population between of the origin and the destination destinated neighborhoods, because more populated neighborhoods usually have more opportunities for social interaction. Okay, so if you only consider the distance factor in our mobility model, then we can also only explain a small portion of the super spreading phenomenon. So the Gini index is 0.17. So it is almost similar with the previous scenario, that it means the distance factor in our mobility model didn't contribute to the super spreading phenomenon. Okay, but if we consider this uneven urban population distribution combined with the population factors in our mobility model, then we can explain almost all of the super spreading phenomenon. So we have a very uneven distribution of the secondary infection and the infected population. The Gini index is 0.63, so that's close to the complete model. Okay, so here we can have this. I think we can draw this hypothesis that the super spreading in urban space is a joint product of this uneven population distribution and the social cooperation-driven mobility. It means the population are distributed unevenly in the neighborhoods. Some of the neighborhoods are more dense, so they have a higher risk. And more importantly, those neighborhoods will also attract more mobility flows from other neighborhoods. So they both contribute to the super spreading events in urban space. So okay, so right now we in these figures we try to show that our model show the potential application of our model. We try to analyze that whether it can be used to devise some cost-effective mobility reduction policy. Okay, suppose we have a given budget of lockdown population. Suppose we can lock down like 10% of the overall population in a city. That's a hypothetical scenario. Okay, so if we use this budget in 3 different ways. So if we randomly selecting some neighborhoods, okay, if we randomly selecting some neighborhood, then we will have this green line here. So the y-axis is the percentage of the reduced infection, and the 0 here is the baseline. It means we do nothing. We do nothing. Okay. So the green line of randomly selected some neighborhood is actually close to the baseline here. So it means we randomly maybe lock down the neighborhoods of 10% of population. We virtually have no effect. So the number of confirmed cases is close to the real world scenario. Okay, so if we choose to lock down the top populated locations, that makes sense, right? The top populated locations are usually the most dangerous ones because there are more people there, right? So if we choose this straightforward policy, then we can approximately reduce like a 21% of the overall infection when overall infections. Okay, so however, if we choose the most infectious location predicted by our model, so our model not only consider the population distribution, but also consider the potential mobility behavior in urban space, then we can reduce like a 45% infection. That significantly outperform the baseline strategies. And okay, I think there are some. Maybe I can answer the question in the chat box when I go through the slides. And here I show that our model can also be used to evaluate maybe some counterfactual scenarios. So like the what if scenarios, what if the intervention policy are implemented at different time or at with different level, like 10% higher quarantine rates or 10% lower quarantine rates. So we can show that what we have, we can try to predict what will happen with different hypothetical scenarios. So so here we will quickly summarize the main takeaways of this the first part of the talk I want to share. So the fine-grained intra-city mobility behavior is essential to explain the complicated and distinctive COVID-19 growth curve in cities. Okay, the superspreading phenomenon is a joint product of the uneven population distribution and the social cooperation-driven mobility behavior. And we show that a metapopulation epidemiological model coupled with an intra-city mobility model can adequately reproduce this growth curve and the superspreading phenomenon. And our model can potentially help to devise some cost-effective mobility reduction policy and intervention, and to evaluate some hypothetical scenario of the intervention policy. Okay, that's the first part of my talk. I think maybe I can take some question now to answer the first part, and then I will jump to the second part. Okay.
Andrew, do you want to jump in and ask your question?
Yeah, sure. Hey, this is super cool. I think this is very interesting, and I was just wondering if you've looked at kind of other properties or what characteristics the neighborhoods that are the most infectious share, at least in terms of what your model predicts, versus stuff like crime, housing density, income inequality, those types of kind of classic SES socio-demographic factors.
Okay. Okay, I will jump back to the. So the most infectious locations. So okay, so we all know that the more populated locations are more likely to be dangerous. So because so you are more likely to be exposed to infected individuals, right? So but in our models we also have this mobility flow between the neighborhoods. So the other dangerous location will be the the neighborhoods that are close to densely populated neighborhoods. So because we predict the mobility flow between them are positively correlated with the population size and the and inversely proportional to the distance between them. So if you are not in a densely populated neighborhood, but you are close to one, then maybe you are also more dangerous that neighborhood, because they are more likely to have a large mobility flow with the city centers or with the populated neighborhoods. Yeah, that's the neighborhoods that cannot be identified by only look at the population and density. I think. Yeah.
Thank you.
Yeah.
I'll ask a question, Fengli, which I suspect other people in our community would ask you too, which is that I appreciate, of course, that sort of the mechanics of the models are that you have these interaction terms driven by mobility, and this is what you're implementing. But we actually know from many other studies, some of them case studies, some of them very dedicated, like in hospitals, that obviously it's not mobility that transmits the disease, and it's not even in just generic interactions. It's really the kind of interactions that people have or don't have, even as they are sometimes at high density and at high risk. And those, people have tried to explain why certain communities at similar densities and similar transportation patterns would take more of a toll from disease or not. And whether this has to do with behavior, people believing or not believing in the disease, whether it has to do with pre-existing conditions and poor health, sometimes connected to poverty and other factors. So there are many factors like that that also seem to be important, and also civic behavior, whether people are willing to actually take behavior that's preventive on behalf of the community. This is very important, for example, for younger people. So all of this is not quite in your model. So you're working in certain aggregate ways. And so I think Andrew's question was also a little bit touching on that. In Chicago and many American cities, we know these factors are important. So what would you say to that?
I think that's a very good question. That's a very interesting point. So I think, here in this research, we proposed like a simple, or should we say a general framework to try to rationalize the growth curve of the confirmed cases. Yeah, I think, of course, it will help if we can have like a more we can characterize the feature of the urban environment and the feature of the population more fine-grained, right? Like maybe the income or the occupation type of the individuals, because there's some previous research showed that the disadvantaged group are more dangerous in this pandemic because they need to go out. They cannot stay at home. The level of mobility, their mobility reduction is lower than the rich population. They need to go out to.
Fengli, sorry, just in the interest of time, since we don't have a lot of time left, could I give you about 5 minutes to talk about the rest of your talk? It's not a lot of time, 5-7 minutes, and then we'll have some questions at the end. But I cannot stay over the hour, and I think others cannot either. So go ahead.
Okay, so I should jump into the second part of my talk, right? Okay. In this second part of my talk, I want to briefly introduce some previous work, project of mine, and one ongoing project I'm doing with Louis here. So I want to initiate some cooperation with our lab mate here, or So some of my previous work have been to look at the interaction, the connection between the macro level city structure and the micro level human mobility, or shall we say human behavior. Okay, this is the land use planned for Shanghai city. So obviously they kind of correlate with each other, right? So the land use plan kind of decides how you go to different parts. Why you go to different parts of the city? Why you go to a place? Because I want to go there for movies or for dinner, all right? And I think ultimately the mobility behavior will also shape the city structure in the long term. So okay, so in one of my previous work, I try to analyze how the microscopic individual mobility behavior can impact on the macro level city structure, on the city morphology here actually. And urban scientists, they predicted the urban will grow like homogeneously in a perfect city, like the future garden city over a century ago, which contradicts with the fractal morphology. The fractal morphology is like a coastline we observe in current empirical data. So this is the population heat map of the London city. We can see that the edge of the city is very uneven. It's like a coastline. So the scientists believe it is because of the bottom-up mechanisms, which is still largely unknown. So as a basic element of the cities, so how does the individual cities mobility behavior can reflect in the urban growth patterns? Can the individual mobility behavior be the bottom-up mechanisms of the growth of cities? So that's one of my previous work. So I would skip the details and jump to the conclusion. Okay, so our analysis find that the existing mobility models can be classified into a paradigm of 4 categories based on whether it can consider the memory of previous mobility behavior or whether it consider the social interaction between different individuals. Okay, our theoretical analysis indicate the urban growth patterns can only be reproduced when there is both a strong social interaction and the mobility memory. But in this is the missing corner here. So to fill in the gap, so we propose collective mobility model CNN. It has a preferential exploration. It means it has in each step you have some probability to explore a new location. So the probability of exploring new location is the gravity model, right? Like the model I just used in the pandemic model. So it can capture the social interaction based on the population density there, and it will also have a probability to decide to return to a previous location based on the previous visiting frequency there. So if you want to see the details, you can look at this paper. It's online now. I think it's not published yet, but you can find it online now. So we show that in our CNN model, indeed can reproduce this morphology of this empirical city is like the fractal morphology, and we can also reproduce some empirical laws of the city growth, like the scaling law in cities. You can see the red dots here of a model can reproduce the scaling law of city with the right exponent of -2, and the superlinear population growth with city size, and the exponential decay of the population of urban areas density. So that's my previous work on how individual mobility model might impact on the urban structure, or shall we say urban morphology. And one of my ongoing work with Luis here is that maybe try to understand how the city landscape or also the city structure will impact on the human behavior. So we collect some. We try to extract the city structure and the city landscape from the street view data. So we have many open street view data right now from like by Do Map in China or Google Map in US or in Europe. And then we also have some nice data that have been released by previous researchers. So I've trained this semantic segmentation model that try to extract the city landscape from these street view images. So for example, in this input image, so we can extract the wall here, the purple area, the wall and the building, the black area, and some pavement, some roads, some pavement, and in this input area also we can also this vegetation and yeah, different kind. This is some example. We can extract the landscape captured in each street views. So based on this this model, so we can have a fine-grained profile of the city structure in the urban space, So here is one demonstration. We call it like the wall index, like the percentage of wall in the heat map shows the percentage of wall in the street views of each grid. So we segment the city into numerous grids, and we compute the percentage of wall in each grid. So if we zoom in, we can see that our model can actually capture the wall of forbidden city. So if you have been to Beijing, you will know that the forbidden city is enclosed with a very high wall. So around here they have a dark color. It means they have high percentage of wall. So it means our model can accurately capture the wall here. So in our preliminary analysis right now, we try to correlate the street view feature or the city's landscape feature with the mobility behavior. So we try to predict the visitation frequency of each location based on our street view feature and this point of POI feature. There's an additional feature about the city land use. So we can see that we have some signal here, but the result is not very good. But looking more into it. So in this figure, we can show the importance of different features in predicting this basic mobility behavior, the frequency, the visitation frequency. So we can see that in the street view feature, then the most important one is like the car, the person, and the building, and the road, and the wall, maybe like that. So that's maybe like more like the accessibility of a location that will impact on the visitation frequency there. I think it kind of makes sense. And recently, the Professor Mark Berman had reached out to us. He shared to us some street view data set that are labeled with crowdsourced perceptions, like natureness and the transparency and the disorder and so on. So yeah, I think that's the future direction. As a future direction, I think we want to investigate this project, like how these three elements here might interact with each other. So like how this city structure, like the wall, or maybe the building, or some semantic feature will impact on the cognition or perception, like the natureness or enclosure or dangerousness of a place, and how that will translate into behavior, like the mobility, social interaction, or crime in the cities. So that's the basic the high-level roadmap of this project. And I would love to discuss with you if you have some suggestion about that. Yeah, thanks.
All right, Fengli, thank you very much. So that's very interesting, with many, I think, things to follow up and also to just think about in terms of collaboration. So I know we're very short on time, and with apologies to you and to others, I'll have to jump off at 10 because I have sort of a thesis examination that I need to be there on time. But if there's any questions, please jump in and ask. We probably have time for one question, a quick question.
Actually, following Andrew's question, this is Bob. Thank you for our presentation, interesting presentation. I just wonder, how do you define these neighborhoods?
Okay, so we have several ways of dividing them. So in our previous work, we just divide them based on grid, like a 100 meters times 100 meters. So one or a more, maybe a more natural way is to divide them based on the road network. So we have done that in other projects. Like we can extract the skeleton of the road network, and we can segment the city into like the street block based on the main road. So I think that will make more sense. Yeah.
Mm. Thank you.
Right. So one thing is that really this kind of data that Fengli has for Beijing, which is interesting, I'd never seen it before, is also becoming so much more available all over the world. Of course, we've had it in the US for a while in terms of street view. You can create your own street view. Some applications allow you to do that in environments where you want to do it, particularly places that don't have cars. But for example, I was just looking at street view for Lagos, Nigeria, that Google created, and it's exceptional.
Yes.
It's really amazing. I mean, it's a city like you've never seen before if you're used to US or Chinese cities for that matter. And you know, so there are a lot of possibilities to think about this interplay between, you know, sort of almost more microscopic person scale elements of the city, and yet bring all this technology to it. So it's a very interesting interface that begs a lot of questions. Fengli can do it.
Yeah, I think it would be super interesting to look at like a more interesting place. Yeah.
Fengli, how do people find you?
Okay.
They
Yeah.
want to
Sure.
talk more.
In my last slide. Sorry. Okay. Sorry. Oh, my screen frozen. Wow. Yeah, you can find me in this through this email, and you can also find me in the phonelish.com. It's the homepage of, yeah, it's my whole homepage. You can say, yeah.
Thank you. That's great. And soon you'll be here, right?
Yeah. I think I will be there by the end of this week if it all goes smoothly. Yeah.
Good. And hopefully it'll be possible to start working in person sometime soon.
Yeah.
Okay, everybody, I'll jump off. Thank you, Fengli. So interesting to see all the things you're doing, and obviously all the possibilities that they also open. For me, I'm gonna log off, but if everyone wants to just stay on, I don't know if Fengli can, but
Yeah,
we're reaching the end of that. Yeah,
I'll stay on. If you have more questions, then you'll be most welcome. Bye.
And thank you everybody for joining also. I know Fengli, it's probably midnight for you in Beijing. So.
No, it's okay, yeah.
All right, wonderful. Well, if there are no questions, again, we just want to thank everybody for joining our lunch colloquium. We'll have another in, I believe, 2 weeks with Jared Schachner on March 10th. So stay tuned for that. But again, Fengli, thank you so much for your presentation, and it was great to see you. So
thanks for time.
Okay. Thank you, everybody. Take care.
Bye.
Bye.
Bye.